few more minutes until 2 o'clock, but I just wanted to let you know we'll be ready to start momentarily. And we'll just give everyone a few more minutes for other attendees to join. And I'll be back with you shortly to introduce your hosts for today, Nandish and Vivek. And we look forward to a good discussion this afternoon. Thank you, and we'll be back in just a minute. Hey, good afternoon, everybody. Welcome back. It's just after 2, and so we'll be ready to start our webinar. So again, this is Eric Org from Azimuth Systems. Today we have a webinar prepared to discuss operator benchmarking with DNA, and it'll be hosted by Nandish Chalashazar and Vivek Radakupatu. Nandish is the head of engineering for Azimuth's Analytics Business Unit, and Vivek is responsible for the business unit as a whole. So both Nandish and Vivek have extensive experience with operator test plans, with wireless infrastructure and devices, and with test equipment. So with that, I guess just one note of housekeeping. If anybody has a question over the course of the webinar, please use the chat function available on GoToWebinar to send Vivek and Nandish a question. And then when they find a break, they'll be able to address that question directly. I think there's just a few participants, so we should be able to handle questions as they arise. Okay, well, with that, I'd like to turn it over to Vivek to start the webinar. Vivek, it's all yours.
Good afternoon. Hi, my name is Vivek. I run the Analytics Business Unit at Azimuth. So thank you for joining us this afternoon. Hopefully you're able to see our slides. So before we get started, we wanted to give you a very quick introduction to Azimuth Systems. Azimuth Systems was founded in 2002, and we've been at the forefront of technology. Azimuth's product portfolio is essentially, there are two main pieces to our portfolio. One part of it which focuses on RF channel emulation and real-world playback. So these are our ASMX, SRNX, and field lab solutions. And a complementary piece which actually allows us to take data generated through these test solutions and make sense out of the data. This is automation and analytics piece, and this would be the focus of today's discussion. Moving on to slide 3. So if you look at challenges today, we spoke a lot to operators, and one thing operators tell us is how many times they get data from, it could be industry sources, marketing sources. This is benchmarking data, comparing them to other operators, or sometimes it's comparing the performance of different devices. And typically, even as a common user, you would find this many times where typically once or twice a week, you'd find these reports where they tell operator A did very well, operator B didn't do that well. So then you ask the question, there are so many reports that are being put out, what is the actual value to a customer? When we went and spoke, we did a survey where we spoke to some leading tier 1, tier 2, and tier 3 operators in the US and internationally. And the feedback was, there are a lot of these studies that are being done, a lot of data being generated, but the actual usable value for the customer is questionable. What do I mean by usable value? What I mean by that is, it's one thing to tell that operator A is better than operator B. So if I'm operator B, I know that I'm not as good as operator A. Something is usable when I'm able to take this data and figure out what are the next 3 or 4 things I need to do so that I become better than operator A. And in the survey we did, the majority of people we spoke to basically told us how they get this data, but the data is not actionable. So then we decided, okay, let's take let's dig into this deeper. Why is it that operators run into this issue? This has been going on for a long period of time, benchmarking. What you find there is there are some shortcomings with the existing way in which benchmarking is done. One of the very common things we find is benchmarking is very, very siloed in nature. And what I mean by siloed in nature is people typically focus on application layer performance. Now, we always start with the subscriber, which is the right thing to do. But what happens is, this is where most benchmarking also stops. People look at the user performance. They tell, oh, YouTube was very fast on network 1, not so fast on network 2. But there is very little focus on the underlying layer. So there's a lot of focus on the application layer, but very little focus on the underlying layers. And the second challenge that you find, which kind of relates to the first challenge, is the fact that you have performance without context. And what that means is, you tell throughput was very bad. But then the question is, if I'm an engineer, the first question I'm going to ask is, okay, performance is bad, but under what conditions? Was this indoor? Was this outdoor? What frequency? What were the RF conditions? What device? So today, in some ways, as a operator, I'm told my network didn't perform as well as my competitor, but you always want to know the context. What are the conditions under which I'm being compared? And then the last thing which complicates the whole situation is the tools that are there. The tools that are there today, while good for traditional testing, are inadequate for the developments in technology. You find tools that are too complex to use, where the user is thrown a bunch of there's a lot of information overload from a user standpoint. Or the other extreme is where you find that the tools just stop at the application layer and don't necessarily tell a complete picture of what's going on. So now I'm sure most of you are thinking, okay, you've told me that benchmarking does not the operator benchmarking data we collect today is not perfect. Yes, I go through that pain as well, and you've exposed the problems with that. So if we were to put aside reality and tell how should I actually do benchmarking, or what is the best way to do benchmarking? So we did a lot of research, and based on the expertise Mandish and the team brings to the table, this is our firm belief of how true network benchmarking should be done. When you do benchmarking, you should do comparison of KPIs or metrics, not just at the application layer, but all the way from layer 1 to your application layer. Agreed that from a subscriber standpoint, what matters is just application layer, but what happens beneath the application layer does have an impact on end user experience. As an operator, if I have to invest more resources to get the same end user experience as another device, that is definitely more relevant to me. So that is the first thing. So the comparison should not just be at the application layer, but it should also be at multiple layers, all the way from layer 1 to the application layer. The second thing is you always should do an apples to apples comparison. What that basically means is you have to compare the devices or the network. In this case, we're talking about operator benchmarking. You have to do the comparison under the same conditions, with the same set of operations, so that you minimize the number of variables. You minimize the number of variables that may cause a difference in result. Then the last thing is, while it's important for us to look at average performance, it is also important that you identify individual outliers. Remember that when a customer runs into an issue, it is always the outlier that really stands out. As a user, I don't think of the 90 times I was able to set up the call successfully. I think about the 5 times when the call dropped for me. So while it is very important that you get an average performance, you run thousands of runs so that there's enough statistical significance, it is also important that you're able to look at performance on an individual basis. So we've taken all this, and that has really been what has driven our methodology. Our methodology, the fundamental philosophy that has defined our methodology was basically to address these issues. We want to make sure that when you benchmark operators, you understand the difference in experience across these operators. Which operator is good for a user for which operation? So that is the first level. The second level of detail you want to understand is, okay, if there is a difference in performance across operators, what is the root cause for that? What is the cost for that difference in performance? And then the last thing you want to do as a part of this, which in many ways is very, very critical and is a big point of pain for existing customers, is you want to provide actionable insights. What that means is, it's one thing to tell operator A is better than operator B, but what actionable insights really means is operator A is better than operator B because of reasons X, Y, Z, and if you were to go and take steps P, Q, R, that would go fix it for you. That is really the process you should follow. So the methodology, as we spoke about, is optimized for true benchmarking. True benchmarking, as we discussed, is something that looks at apples-to-apples comparison across all layers, and gives you visibility both into average performance as well as individual outliers. So then the last question becomes, okay, you've spoken about a new methodology which accomplishes the end goals of what we have in mind. How do you go about doing this? How we do this is through Azimuth analytics solution. We spoke about this in detail in an RCR wireless webinar we did back in October. You can find more details on our website. But Azimuth analytics solution basically consists of 2 pieces. There's an automation piece and there's an analysis piece. The analysis piece is called DNA, Device Network Analysis. And this is basically an analytical engine, a very powerful analytical engine that has the ability to correlate the user experience with underlying device network events. So with that, we are actually going to move on to a couple of use cases that will be covered by Nandish. sorry, we are having some technical issues here. Please hold on.
Hi Vivek, this is Nandish. Can you hear me?
Yeah, we can hear you. Please go ahead, Nandish.
This is the voice. So you just dialed into this number?
Sorry, all, we are having some technical issues. Please hold on.
Or a telephone? Oh, you're connected to mic and speakers or telephone? Just try telephone.
Nandish, why don't you run it off my laptop? That's probably better.
Sure. Can you hear me now, Vivek?
Yes.
Okay, perfect. So,
Do you have the presentation?
no, right now,
Okay.
can I just run it off your machine? Because I think
Yes.
I just need the keyboard and mouse access.
Yes, I'm just giving you keyboard and mouse. Yeah. Okay, I just put it in presentation mode. Are you able to control it?
Yeah, okay. I think we should be good now. Right. Sorry, everybody, for the technical glitch. This is Nandish Chalisazar. Thanks, Vivek, for the introduction on the challenges with operator comparison, benchmarking, and what Azimuth solutions can provide. So really what we want to do now is talk about some real-world case studies where we compared 4 US operators. And the main objective really here was we've seen a lot of press releases where operators have been compared and one operator has come out on top compared to the other 3 operators. And it was a little bit frustrating for us to sit down here and see that these press releases come and talk about different operators and their performances, but nobody really goes into the details of what really causes the performance to be bad for one operator versus what causes the performance to be better for another operator. To us, it seemed like watching a movie where there's a good guy being shown and then 3 other bad guys, but really the movie does not go into explaining what caused the bad guy to be bad, what really can be changed with the bad guys to make them look good, and so on. So really that was our main objective of doing this case study, and we're going to go into some details of what we found in the Boston area with that case study. I'm still not able to move the slide. Just give me 1 second, please.
Nandish, I moved the slide.
It's right now it's on the polling question actually. Can you close the poll because right now the screen only shows the poll. Okay, all right, sounds good. So yeah, so to give you an overview of what we did, we benchmarked the performance of the 4 biggest US operators in the Boston suburbs. What we did was to collect data with our own tools with 4 commercial Samsung flagship devices. The main objective was to pick a Samsung device that's very prominent in the typical user's hand today and do an apples-to-apples comparison of all the 4 operators with that flagship device on the LTE network with these 4 operators. And as I said, the main objective was to try and understand user experience differences across these operators, but to also explain what causes this user experience to be different between the 4 operators. So moving on to the next slide. So the first case study that we want to talk about out of this is we compared the download data speed performance. Now, we all have seen a lot of press releases and even advertisements recently with RootMetrics claims of who's the better operator and who's got the most reliable network and so on. So we took an example of comparing download data speeds, and what we've done is we've tried to summarize some of the key findings in terms of user experience and what causes the user experience in this particular slide. So if you look at the 4 operators, A, B, C, and D, we didn't want to name them for proprietary reasons at this point in time, but really these are the 4 biggest tier 1 operators in the US. And as you can see, the 4 operators seem to have significantly different user perceived download data speeds. Operator A had 6.5 megabits per second versus B having 5.43. Operator C had the lowest throughput in terms of 3.3 megabits per second, and operator D was equally worse as operator C with 3.32 megabits per second as well. So, and this is kind of in line with what RootMetrics and others have reported recently in terms of there being a fairly big gap between the data speeds seen across operators. But we didn't want to stop there, and that's really we want to kind of try and understand in this case study as to what really caused operator A to be the best operator and what caused the operator C and D to be the worst operators in this exercise. And that's why we believe that you need to start looking into the different layers of the protocol stack, the different layers where the device and the network are interacting with each other to cause this user experience. Whether it's the physical layer, the MAC layer, the RLC layer, or even the TCP/IP layer, all of these layers need to be looked at holistically to really understand why throughput was good for operator A versus throughput was bad for operator C and D. And so let's talk about operator A for now. He came out to be the best operator in the Boston suburb region. And if you look at what happened at the physical layer in terms of operator A, the operator A contributed to a pretty good physical layer performance in terms of the physical layer scheduled throughput. What this particular KPI means is, if at all the upper layer effects were taken out of consideration, if you are not limited by backhaul or if you are not limited by your FTP servers and so on, what kind of speeds are you perceiving over the air whenever you're getting scheduled from the network side? And as you can see, operator A had pretty high physical layer throughput, and that physical layer throughput means that as far as the eNode B is concerned, as far as the spectrum investments are concerned, operator A has done a good job of making use of the spectrum and their eNode B investments to offer an over-the-air throughput that is very, very substantial in nature and pretty much on par or better than most operators that are being compared over here. So physical layer really helped the operator A to offer really high user perceived data speeds. But what helped the physical layer to look so good were multiple reasons. If you look at the control format indicator, the CFI, it was obvious that operator A's network was least loaded compared to all the other 3 operators. So this relatively less loading means relatively less users on the network to compete against the resources. And so having fewer number of users on the network helps to kind of offer better speeds on an average to the test that's being done basically. That also helps from the fact that the number of resource blocks being assigned by operator A is pretty much high, one of the highest compared to the other 4 operators, or on par with operator D. So the fact that the network is relatively less loaded helps operator A to assign more resource blocks, because the more resource blocks that you can assign in LTE, the better speeds you get at the physical layer, and that was helping operator A as well. So lower speeds, higher resource block assignments, and spending substantial amount of times on the LTE network really helped operator A to offer the best performance compared to the other 3 operators. If you look at operator C, which was one of the worst operators in this comparison, as you can clearly see over here, the physical layer speeds were definitely lower for operator C compared to any of the other operators, which means that operator C seems to have problems in over-the-air throughput itself. Even if you don't consider the backhauls and other speeds, just in terms of the physical layer performance of operator C, it seems to have come out significantly worse compared to the other operators. And some of the reasons why the physical layer speeds were lower for operator C was because of the fact that operator C was having the UE camp on a relatively low bandwidth LTE carrier. Operator C, one of the LTE carriers, has lower bandwidth compared to the other operators, so only 20 resource blocks could be assigned to the end user on an average in the operator C's network compared to the other operators' network. Another big factor that really impacted operator C was the fact that the percentage of time that the device spent on the LTE network was only 40% compared to about 90 to 100% for all the other operators. So it looked like even though operator C had deployed LTE nationwide kind of thing, its devices were spending significantly lower amount of time on the 4G network, and they were spending quite a bit of time on the 3G network, because of which the speeds that are being perceived by the end user were lowered. And so that kind of starts giving you some clues as to why operator C was the worst operator. Clearly, the top 2 or 3 reasons for operator C to be the worst were the fact that the device was spending lesser amount of time on the 4G network. The other reason being that the coverage offered by operator C was relatively poor compared to the other operators, and the bandwidths that the operator was assigning to the end user were significantly lower compared to the other operators. So these are the top 3 reasons why operator C came out to be the worst. And so then the next question really is, what causes these top 3 reasons to contribute to low throughput for operator C, and is there anything that you can do about it? And that's really our philosophy of operator benchmarking. We don't want, as we mentioned earlier, we don't want to stop at just highlighting which operator is good versus which operator is bad. What we believe is it requires device network analysis across the different layers of the protocol stack to really help understand the why of why one operator is bad compared to other operators. And in this case, operator C was the worst. And one key thing that stood out in our analysis is that one of the key parameters for cell selection, called QRX level min, which defines the threshold at which the UE would camp on the LTE network, was significantly different for operator C compared to all the other operators. So for example, operator C had QRX level min of -116 dBm, which means that if the signal strength perceived by the UE is lower than -116 dBm, it's very likely that the device would have gone to 3G. Whereas for those kind of signal strengths, the other operators would have still let the UE camp on the LTE network and perceive LTE download speeds during those instances. So clearly this highlights the fact that when you're looking at operator benchmarking performances, you look at different KPIs to look at all the layers of the protocol stack. You try and correlate the performance to different network settings that influence the device network performance, because even if you may have optimized your RF and you may have created a very good RF in terms of signal to noise ratios and coverage, there are still a lot of key network settings that influence how the device interacts on the LTE network, and all of these need to be looked at holistically to really understand what causes the performance difference. And in this example, as we pointed out, this one particular parameter was a key differentiator which caused the UE to spend more time on the 3G network for operator C, and that led to a big degradation in throughput or data speed for operator C. Now, if you talk about operator D, it gets even more interesting for operator D, because as you can see, the user perceived speeds for operator D are fairly similar to operator C, and they're kind of significantly lower compared to operator A in terms of user perceived speeds. But if you look at operator D, the issue did not seem to be related to the physical layer. It seems like operator D, in fact, had the highest physical layer burst rate compared to all the other operators being compared in this drive test. That's interesting, because what this is telling us, we have seen instances where operator D has deployed high bandwidth LTE carriers, and these high bandwidth LTE carriers are leading to pretty good physical layer speeds. And in this case, about 12 megabits per second was perceived by operator D's network compared to any other operator, which is the highest. But somehow those high physical layer speeds or high over-the-air speeds between the base station and the UE are not translating into an end user experience that is good for operator D. it looks like the end user experience is still pretty poor for operator D, even though over-the-air speeds are pretty high for operator D. And that's interesting because typically the biggest challenge for any operator is really the RF challenges. The wireless link is the toughest link to really overcome and offer the best rates for the end user. But it seems like operator D has really solved that problem pretty easily in terms of offering pretty high over-the-air speeds, but it is not translating into a good end user experience over here. And that's again calling for an analysis which helps understand what's happening at the different layers of the protocol stack beyond the physical layer. That may help understand why does 12 megabits per second translate only to 3 megabits per second for the end user. And we'll talk about that in the next slide or the next couple of slides, and that will help provide insights as to what was going on that contributed to lower speeds for operator D. But one thing I want to point out is operator D was helped by the fact that it was able to offer a very high number of resource blocks to the UE. It had fairly good coverage and signal-to-noise ratios compared to any other operator out there, and the device was spending 100% of the time on the LTE network. So as far as the LTE network investments are concerned, they are kind of allowing the UE to spend most of the time on the LTE network, offer very good coverage, offer very high bandwidth carriers to really help data speeds, but yet the throughput is not very good, and that's what we're going to go into the next slide for essentially. But to summarize the slide, as you can see, operator A was the best operator. It was helped by the fact that it had relatively less loading compared to any of the other operators. Operator C and D were the worst operators among the four operators. Operator C was limited by the fact that it was spending relatively less amount of time on the 4G network, which was related to the suboptimal setting for QRX level min, as well as deploying lower bandwidth LTE carriers. And operator D was also one of the worst operators, but the problems there were different from physical layer problems, and that's why we are moving next. So going to the next slide, what we did with operator D was we said, looks like when you look at things from the LTE network perspective, everything looks good. So let's start looking at the higher layers, like the TCP/IP layer, to really understand, when over-the-air speeds are high, why is that not leading to good user experience speeds? And so we took some examples where you said, okay, let's take typical FTP downloads where the downlink user perceived speeds was about 3.6 megabits per second. And in that same example, we saw that the network was offering a speed of 23 megabits per second at the physical layer. So this is again going back to the average speeds we were showing earlier, where physical layer speeds are high, but user perceived speeds are lower. And in this case, again, we found that the UE was spending 100% of the time on the LTE network. The RSRP average was pretty strong. The signal-to-noise ratios were very high, which explains why the physical layer speeds were very high. And one thing we noticed was, in terms of the time domain, the subframe usage was significantly lower. So even though the physical layer speeds are very high, it looks like when you look at a 10-second download, only 1.7 seconds of the download are being scheduled or are being used by the LTE network for sending the data transfer. And pretty much 8 seconds of the data transfer, there is no data coming in from the network. That's what the subframe usage really means. And that triggered us to look at the TCP/IP layer to understand how did data transfer from the network to the UE at the TCP/IP layer. And this is where we are showing a typical TCP trace analysis. What this TCP trace shows is that this is a 5 MB download. So from 0 to 500 KB to 1 MB to so on, up to 5 MB. If you look at the TCP sequence numbers, how did data come in as time moved along? So the x-axis is the time axis from 0 seconds to 11.5 seconds in this example, and the y-axis is the TCP sequence number, which is 0 bytes to 5 megabytes on top, essentially. So this is showing you how data is coming in from 0 MB to 5 MB as time moves along. And when you look at this picture, there is some trace of TCP stalls or TCP situations where no data is coming into the UE, and that next slide will show you the zoomed in version of the section that I'm showing. It may not be obvious from this slide directly, but it at least is pointing out to the fact that it took 11.5 seconds to finish this download, and it was a 5 MB download where the data didn't seem to be coming continuously throughout the download. The next slide, which shows the zoomed in version of this TCP trace, it becomes more obvious as to what the issue is that contributes to low user perceived speeds but high physical layer speeds. As you can see in this example, it looks like, data comes in chunks to the UE. There's a fast transfer of data, and then there's a period of time when there's no data coming into the UE, followed by a period where data is coming in at high speeds, followed by a time where there is no data coming into the UE. So this is what I call as a TCP stall, where data does not come into the UE for a certain amount of time, followed by a huge splurge of data coming into the UE. And when you look at the details over here, we saw that this length of data bytes that were coming in together was about 64 kilobytes. And then there were about 100 millisecond stalls in data transfer, followed by another 64 kilobytes of data coming into the UE. And when you go back and look at the TCP trace, it became obvious that the TCP window size that was being used by the Samsung flagship device was set to 64 KB, whereas the other operators had much higher TCP window sizes. And typically what TCP window sizes do is it helps to kind of open up the buffers to help the transmitter or the network to send chunks without having buffer underruns in the network. If your TCP window sizes are very small, then that would mean that the physical layer may transfer the data very fast, and before the acknowledgement reaches back to the server, the new data is not coming back because you underrun your buffers. Your buffer is already emptied from the base station perspective, because the base station and the UE are able to transfer data very, very quickly, but the network is not sending a lot of data without being acknowledged, and because of that, there are these stalls in data transfers, and these stalls in data transfers is what causes the throughput to be significantly lower for operator D compared to all the other operators. So again, clearly highlighting the fact that looking at TCP/IP layer analysis, looking at the different layers of the LTE protocol stack are critical in terms of device network interaction, and to understand why one operator is worse compared to the other operators, and really taking the right actions from there to help improve operator performance and hence deliver a better value to the end consumer who's paying quite a bit of a hefty price tag for the data plan today. So really, this again highlights the importance of operator benchmarking with a focus on understanding the why of why one operator is different from another operator, beyond just explaining who's best and who's the worst, essentially. Okay, moving to the next slide. So this is another use case from the same data set. We really have a lot of use cases that we could talk about today, but in the interest of time, we've tried to keep the use cases to some interesting use cases. What we believe is when you look at the end user experience, you need to correlate that to at least put 100 different KPIs that we look at the different layers of the protocol stack. And all of these 100 KPIs are not for the sake of showing that we can come up with all these KPIs and generate reports with KPIs. The whole idea is to look at the different layers and the critical KPIs for each layers of the protocol stack, and understand how we correlate the performance of these different layers, and how do these different layers interact with each other to help understand the end user experience or the end network experience for the end consumer. So the second case study over here is more related to battery transmit power comparison. So obviously, when you're doing these downloads and uploads during your operator benchmarking test, it's important to understand what kind of transmit powers are being used by the UEs on these different networks, because if the transmit power being used for data transfer is very high for one operator compared to another operator, that could mean that the battery drain or the battery life of the same UE may be poor for one operator compared to another operator. So beyond just the typical battery life experience test, we need to understand what kind of battery transmit powers are being used by the different UEs on the different operator networks to understand why that happens, and is there anything that we can do about it. So in this example, we compared the PU-CCH transmit power and the PU-SCH transmit power. The PU-CCH transmit power is the control channel transmit power that the UE sends out for sending control signaling between the UE and the network. So even if you're doing FTP downloads, there's a lot of control signaling that goes from the UE to the network, and all of that control signaling goes over the PU-CCH channel typically. And if you look at the table over here, it becomes obvious that even though the coverage is kind of similar between operator A, B, and D, for the purpose of this analysis, I think we should ignore operator C. The reason being we ignored the performance of operator C is because what we were showing earlier, where operator C was spending considerably low amount of time on the LTE network, so majority of its time was spent on the 3G network. So the averages that you see here would not be apples to apples kind of averages. So really we can ignore the data for operator C, because most of the time of operator C was spent on the 3G network and not on the LTE network. But if you look at operator A, it becomes obvious that operator A was the one which had the least amount of PUCCH transmit power compared to operator B and operator D. And it was about 2 to 3 dB lower transmit power on PUCCH compared to B and D. And that's actually a good thing, because using lesser amount of transmit power would mean that it can offer a better battery life to the end consumer. And so in this case, we would say that operator A was the best operator in terms of both throughput or data speeds as well as battery transmit power performance. But then the next question is, why is the battery transmit power of operator A better compared to other operators essentially? And as you can see, it's not that the operator A had particularly good coverage compared to operator B and operator D. In fact, operator A was actually perceiving relatively poor coverage compared to operator B and operator D, but yet it was able to manage to send lesser amount of power on the control channel without impacting radio link failures or connection failure performance essentially. And when you start digging into the details, this is where you start looking into end-to-end protocol stack. You start comparing parameters of the different operators to try and understand how parameter settings influence the transmit power comparisons. It becomes obvious that when you look at the settings of operator A's PO nominal PUCCH setting was minus 117 dBm compared to minus 116 and minus 114 for operator B and D. And what this means is this is a base station setting which says what kind of powers that the base station wants to perceive from the UE when the UE is doing data transfer. And the requirement from operator A seems to be less compared to operator B and D, and that lesser requirement has not led to any impact in terms of radio link failures or connection failures. So it looks like with the settings that were being used by operator A, it was able to achieve lower transmit powers, and that helped for the operator A to come out as the best operator in terms of battery transmit power comparisons. Similarly, for PUSCH transmit power, which is the shared channel transmit power, and PUSCH is the channel that typically carries the data packets for the UE. It can carry some control signaling as well, but majority of the power that's being used on PUSCH is typically driven by the data packets that are being sent by the UE to the network. And if you look at the PUSCH transmit power, and it's important to look at the PUSCH transmit power in relation to the number of resource blocks that are being used for sending the uplink packets, because if an operator is sending more uplink resource blocks, that means that it gets done with the data transfer quicker. And operator A clearly is the operator which is offering more uplink resource blocks compared to all the other operators in terms of operator B and operator D. And even though the number of resource blocks are higher, and typically higher resource blocks may mean higher power usage, but despite the higher resource blocks, the power per resource block offered by operator A is lower compared to operator B and operator D. And that goes back again to the PO nominal PUSCH setting. So this is another power control setting that influences how the UE transmits power on the uplink. And when you look at the PO nominal PUSCH and the fractional path loss settings of the network, they are about 3 dB lower for operator A compared to operator B. And operator D, you cannot make a direct comparison because they use fractional path loss, but it is obvious that operator A has the least aggressive setting in terms of power control for closed loop power control, and that has helped the operator A to kind of use lesser amount of battery life or lesser amount of battery transmit power and offer a better performance to the end consumer on the network essentially. So again, this is an example that highlights how looking at device network analysis holistically helps understand operator comparison and drives the right actions based on the insights that are provided. Go to the next slide. This is the last case study in terms of the operator comparison. So here what we did was we also wanted to understand the signaling events. Obviously when operators are being compared, everybody does a good job of comparing them for throughput and data speeds, but from an operator's perspective, they really need to understand that for doing the same number of FTP downloads or YouTube downloads or web downloads, is it perceiving the same amount of signaling or the required amount of signaling, or is the signaling load on the network going to be very high? And that's the comparison that is shown here in terms of how many RATS connections, RRC connections, and handover requests were being made by the different operators during these drive tests, where we did an apples-to-apples comparison of the same number of FTP sessions, web sessions, and video sessions. And clearly what we found was operator A was making significantly more number of RATS connections on the network compared to all the other three operators, which is actually a bad thing, because having more signaling on the network would mean that your core network elements or your elements on starting from the E node B to the MME to the S gateway has to start processing more and more of these signaling events, and the operator would have to make more investments to keep up with the signaling load. Keep in mind that this is data from just one UE, so if each UE is causing more signaling, then with millions of UEs, that operator's network can become very overloaded with signaling connections. And so we should also be comparing the signaling events and signaling performance beyond just looking at data speeds and battery performance and so on. So in this example, it becomes clear that operator A is the worst in terms of signaling events. However, to help understand what was going on here, it became clear that operator A was having more number of RATs connections because it had more number of intra-frequency handover requests compared to all the other three operators. And that may point to a more dense deployment for operator A compared to all the other three operators. So in this case, it may be just the artifact of how the network has been deployed based on the operator's challenges, but at least if there are issues with YouTube downloads where one operator was perceiving more signaling than other signaling, these kind of comparisons, looking at things on a holistic level, will help identify issues both from a network perspective as well as from an end consumer perspective, and drive the right actions to kind of make the operator better and offer a better end user experience. One other last case study that we wanted to kind of quickly go over was a VoLTE case study, because VoLTE is very kind of important in the network today. In this kind of a VoLTE case study, what we did was we found that right now we're not finding all the operators deploying VoLTE in Boston, but at least for one of the operators where VoLTE was deployed, we found that the phone that was being used, or the Samsung flagship device that was being used, was perceiving a lot of dropped calls during certain drive routes. And we want to understand through device network analysis what was really causing these kind of VoLTE drop calls. And the peculiar symptom of this VoLTE drop call was that we would see VoLTE call drops, but we would not see LTE radio link failures, which means that from an RF perspective, we did not find any LTE radio link failures, but we were seeing VoLTE call drops and one-way audio issues during the drive test. And so we said, going by our philosophy that you should look at things holistically, look at things at the upper layers as well as the lower layers to help understand and explain the answer to the why question. We looked at the physical layer by looking at the RF conditions of the call drop. We looked at the block error rate and how physical layer bytes were coming in for the VoLTE call. We looked at the upper layers in terms of RLC layer and RTP layer, and it became obvious to us as to what was causing the call drop, which is what we'll go over in the next couple of slides. So on the next slide, what we're showing here is for the one-way audio issue, we looked at the physical layer performance, and as I mentioned earlier, the physical layer looked pretty good to us in terms of RSRP and signal-to-noise ratio. We did not see any LTE radio link failures, but what we did see is a VoLTE call drop happening at this particular point in time. This is where the call really started, which is a sip and white. It was followed by a ringing. This is where the call was answered, and this is where the physical layer audio bytes or audio packets started coming in. And the blue line and the green line are the two phones that are involved. This was a VoLTE to VoLTE call. So the blue line, or the red line and the green line is showing you how the physical layer audio packets are coming into both the UEs. And it's clear that throughout the duration of this call, both the UEs are constantly receiving audio packets from each other, and there's really no issue at the physical layer before the call drop is declared at this particular point in time. So this is clearly not a physical layer issue as such. Go to the next slide. That's why we start looking at the next layer in the chain. So if you look at how packets go from the network to the UE, they first go at the physical layer, and from the physical layer, these packets are transferred to the RLC layer. And if you look at the RLC layer trace, which essentially identifies the arrival of packets from the time that the call was established, you can clearly see that this is pretty much a linear line for both the green line and the red line, where both the phones are constantly getting packets at the RLC layer, and so the RLC bytes are constantly incrementing before up until the point of the call drop. And once the call drops, then the line flattens out. But at least before the call drop, there is no stall or there is no stoppage in data transfer for this VoLTE call. But then when you look at the RTP layer, and that's the higher layer in terms of the real-time transport protocol that is being used for VoLTE calls, it becomes clear that as far as the red phone is concerned, the red phone was receiving all the RTP packets fine up to this particular point in time, but 10 seconds before the call drop, which is typically the VoLTE call drop timer, there was no RTP packet coming into the UE for the red phone, But as far as the green phone is concerned, the green phone was constantly receiving RTP packets throughout the duration of the call, and there were no issues in receiving packets at the RTP layer for the green phone. But for this red phone, because there were no RTP packets being transferred from the RLC layer to the RTP layer, that's what led to the stall in the data transfer for VoLTE call, and that led to the VoLTE call drop being declared. So clearly, these are things that identify that it's not always the network that's the problem. One of the fundamental challenges when you're looking at benchmarking and comparisons is you want to first isolate whether this is a device issue versus a network issue. Once you know that it's a network issue, then you want to understand what contributed to the network issue. But at least you first need to identify whether this is a device issue or not. And what this case study is pointing out is that in this case, the network seems to be doing fine. Even at the physical layer, everything seems to be doing fine. But at the RTP layer, there seems to be packet drops going on. And that led to the VoLTE call drop and poor user experience for this particular use case study, essentially. So that's really the last case study that I had. I'll hand it back to Vivek now to talk more details about Azimuth's benchmarking services.
Okay, thank you, Nandish. So before we get started, I quickly wanted to start another poll. I'd appreciate if attendees could take time to respond to the poll. Okay, so thank you for those of you who voted on the poll. So far, Nandish spoke about two use cases. One around the operator comparison that we did. I know initially we told this webinar was going to be about operator comparison, but one thing we've heard a lot from customers is both operators as well as suppliers is how as VoLTE is being rolled out, people want to know what are the issues you're seeing on the field, how did other operators deal with it, which is why we wanted to talk about VoLTE case study. Okay, so let's move on to the, let's try to wrap this up. So far we spoke about how there is a legitimate need in the industry for holistic benchmarking, and that's really been what has been driving our focus as well, both from a product as well as a service standpoint. Our focus has been around providing holistic end-to-end analysis. So the services that we're talking about here are services to benchmark devices, network, or infrastructure, or validate new technologies. For example, you're rolling out VoLTE, you're rolling out carrier aggregation, CSFP. We've been engaged with a couple of operators in the US as well as in other parts of the world in rolling out new networks, new technologies. And typically the service is an end-to-end service where it's not just a question of specifying the test cases, it's not just analyzing the results, it's really an end-to-end integrated service, right from recommending the test cases, conducting the tests on the field, collecting the data, and it's critical that these are done together, because what you don't want is you give data to someone to do the analysis and you hear the person telling, oh, the data was not collected the right way. That is really why we've taken an end-to-end approach where we recommend a test case, conduct the test, collect the data, and then really, if you remember what I mentioned and what even Nandish reiterated, the value of this solution or this whole approach is in the actionable insights we are able to provide at the end of the day. And the actionable insights is basically to tell you operator A, operator B, operator C, who's the best operator, who's the operator with room for improvement, and what are the things that the operator should focus on in order to improve their performance. And one question that people often ask us is, okay, everyone talks about benchmarking, so what is unique about this, or what is different, or are you just another person who's doing benchmarking? And when we decided to start doing benchmarking or any kind of services, not just because we wanted to do it, but more because there's a legitimate need in the market. There is an unmet need, and this diagram in many ways conveys the value proposition or the differentiation of what we are trying to do. Typical benchmarking services, as you already mentioned, focus on the application layer right here. What does the user see? But the real way, the right way to look at benchmarking, or for that matter, even any analysis of performance, is really an end-to-end view where you go all the way from the device to the node view, and you go from layer 1 to the application layer. That is really where you see a difference, where any kind of benchmarking we do, the focus is all the way in going from layer 1 to the application layer. And this is what allows us to reveal the what and why of performance differences. That is, what is different and what is causing this difference in performance. So summarizing whatever we've covered so far, we all know technology is getting more complex. Whether you're an operator, an infrastructure vendor, OEM, chipset vendor, I'm sure all of you are on the receiving end of this. Technology is becoming more complex, and what you find is existing benchmarking solutions are not adequate for this. Existing benchmarking solutions stop short. They just tell there is a difference in performance. There is no way for you to take actionable insights. That is where there is a critical need in the industry for holistic benchmarking to understand the difference in performance and take corrective action. And that is where we've been engaged with a couple of operators and ecosystems to help them roll out the most optimal network, optimal from a customer standpoint in terms of speed, in terms of actual user experience. Then obviously reliability. It's one thing to have a network that performs very well under corner cases or typical cases, but then there are a lot of issues. The outliers, if you remember, is what impacts user experience. So you also want a network that is very reliable in nature. And obviously all of this has to be done with the best ROI from an operator standpoint. And what that means is, it's one thing for an operator to tell, I want to get the max throughput, and the way I'm going to do it is by deploying or setting up 10 new cell sites. Now, that is not a very good ROI from an operator standpoint. So the real magic, or in some ways, it is a trade-off between how do I give my users or subscribers the best network with the best speed, the most reliable network, but at the same time in a manner that is scalable for me, which ensures that I get good ROI. So that is what we wanted to cover today. We wanted to see if any of you had any questions. Okay, so I think let's walk through a couple of questions here. Mr. Jonathan had a couple of questions. So Nandish, first question was, how do you know that operator D's lower throughput is due to TCP and backhaul issues?
So like I was mentioning in that presentation earlier, right, like what we saw was the physical layer speeds were pretty high. In fact, it was the highest compared to the other operators. And then we kind of started digging into the TCP layer analysis, and that's where it became obvious, like I was showing earlier, where the TCP window size that was being used by the phone was 64 KB, and we were seeing that data bytes were coming only in 64 KB chunks. Even though the physical layer speeds are about 20 megabits per second, and accounting for a round trip time of about 50 to 100 milliseconds, you would need at least 200 kilobytes of TCP window size. The TCP window size should typically be set as the product of the bandwidth and the delay in the network. And with the speeds that operator D was perceiving, they should have been setting a TCP window size dynamically to at least about 200 kilobytes in order to perceive better user experience speeds. And since we were able to prove that at the TCP layer data is only coming in 64 kilobyte chunks, and the data is getting stalled after that, that became obvious that this is more of a higher layer issue and not really a physical layer issue, essentially.
Thanks, Nandish. I think there's one more question. The question is from Mr. Russell. The question is, since the TCP behavior was specific to operator D, does this mean that the device used to test operator D was different from the device tested with other operators? I think the reason for the question being, if it was the same device, it would be the same protocol stack.
Right. So I think what we want to confirm is, when we do operator benchmarking, we do make sure that we're using the same exact model of the device, and we don't modify any software on the device when we're doing this benchmarking. So these are all flagship devices that were picked up from the store, We made sure they were the exact same model of the Samsung device as well. So we are very particular about making sure that this is not an S5 versus S4 versus S3 comparison. It was exactly the same flagship model for all the 4 operators, and they were off-the-shelf phones from the operator network, from the operator store, and we did not modify any software before we went out and did this drive test. So this is not related to this not being an apples-to-apples comparison. We did make sure that this is the same exact phone model for all the 4 operators that were being tested, essentially.
Okay. And I think, just to clarify, Nandish, I think, so we got the same model device, but it is a different device for each operator, right? Meaning, let's say I have model X. So typically, at least, we find the OEM might take the device and modify that particular device based on the operator's requirement or their guidance, correct?
That's correct. That's correct.
Yes. So it is the same model device. It is just that from operator to operator, we bought a operator-specific version. For example, if I took the Samsung Model S, the Samsung Model S for AT&T would be different, or a little bit different, would have been modified from the Samsung Model S for Verizon, and that is really the difference between the 4 devices that we have. Okay. So if there are no more questions, we'd like to thank everyone for taking the time to attend this meeting. We will we'll follow up with you with some of the slides that were shared today. Thank you.
Thank you.